Okay, let's get started. Welcome to week 2 of the deep learning course. So the topic of today is convolutional neural networks. Today's lecture will be shorter than week 1. It's divided into 2 parts. Part 1 is giving you an overview and a feeling for what a convolutional neural network is and what it can do for us. And then part 2, I dive into the details about the different layers, the different architecture components in the convolutional neural network. Part 1. So we continue our walk through the different neural network architectures. So we've now reached the convolutional neural network part. Here is kind of the classic task that convolutional neural networks has excelled in, the so-called ImageNet classification task. So the task is that you are given an image. So here are 8 examples given, and then you have to classify each of the images into 1 out of 1,000 categories. And we are given 1 million training examples, so that means 1,000 training images for each class. And for historical reasons, there are something like 250 different types of dogs there. And you can see this system here, we have built a probabilistic classification system. So you can see that the bars indicate the probability we assign to the different classes. So for example, the first image is an image of a mite, and you can see that mite is top hit, and it has somewhat higher probability than a black widow, a spider, and so on, and other insects, and a starfish is on the top in the top 5. So usually when we measure the quality of the ImageNet classification task, we look at whether or not the right answer is in the top 5. And when we see the different error rates, then it's in this top 5 task. But of course we could also have defined a top 1 task. And you can also see that if you take the example with the cherries, that actually the network has done something sensible. It has classified this as a Dalmatian because there's also a Dalmatian in the image. So this shows actually that sometimes it's the answer is ambiguous. And of course humans are very good at this kind of ambiguous answering and can understand the context. And to some degree, a neural network can also do that. Yes. So a little bit about the convolutional neural network on a high level, and then we'll get back to the details a little bit later in part 2. So the idea in a neural network, convolutional neural network, is to do a lot of weight sharing, and we do it in a way such that we can extract features from the image, if that's the input, in different locations in the image. So the same kind of weights are applied in different parts of the input. And if you think back of last week when we applied a fully connected neural network to not to ImageNet but to MNIST, then we actually learned specific weights for different positions in the input. But here we want to look at a way such that we actually apply the same so-called filter in all positions in the image. And this is what you can see in the lower part of the image. You can see now we have this image of the stack of pencils, and now we apply a filter with this as a 3x3 2D filter. We apply that to the image and produce an output image. So this is a very usual way to actually kind of visualize what the filter is doing. And the way that we actually do the computations is that we start in one corner with the filter, and then we do a element-wise product between the gray values in the image and then the values, the weights in the filter. And if we do that with this type of filter, you can see that because of this specific configuration of the weights, then it will pick up edges that are like 45 degrees. So you can see that kind of the edges in the original image that are 45 degrees in either direction is picked up by this network. So this is how it works, and what is kind of special about the convolutional neural network is that these weights that are in the filter, they are learned from the data. They are not engineered by us. And another operation we have in in a convolutional neural network is called pooling, and I'll come back to that later on. But then the kind of general idea is that we have these filter layers. We learn many different filters. Usually all of them have the same size for a specific layer, and then we have pooling layers, and then we repeat this a number of times, and then in the end we just flatten all the outputs of the filters and feed this into one or more hidden layers of feed-forward neural networks, and then in the end we have, for example, the classification output with a softmax. Yes, and here's the most famous, I would say, breakthrough with deep learning, the so-called ImageNet classification paper which is called ImageNet classification with deep convolutional neural networks by Krzyzewski and co-workers. And this was published in 2010, and after that there's been a huge interest in applying this type of architectures to image analysis tasks in many different aspects, both medical and of course this kind of ImageNet type tasks. And you can find a link here to the paper. And this is kind of a graphic that shows the architecture of the network with all the numbers. I'll come back to that in detail. All the numbers indicate kind of the dimensions of the different filters that has been applied. Yes. So how does these filters that we learn look? So if we, for example, look at the filters we have in the first layer here, I should say now when I've described the filter for the pencil image, then I said that this is just that was like this 3x3 filter with 9 weights all in all. If we have color images, then we have 3 color channels, so that means that we also give the filter an extra dimension, a color dimension, with like one channel for the red and one for the green and one for the blue. So the filters we learn are then the size of the filter times 3 in the third dimension, which is the color image. And then we can render these filters as a color image of the size of the filter. And you can see here that we learn these kind of directional white and black and white stripes, and they correspond to roughly to edge detectors. So that means that, like in the pencil example, they will pick up edges. They will kind of enhance if the output image, if there is an edge corresponding to the direction of the filter learned. And then kind of on the lower part we can see some filters that pick up color contrasts. So this is the kind of filters we learned in the first layer. Now we stack these many layers of filters, and then we can also look at what we learn in the subsequent layers. And here we have an example. We have cherry-picked a specific filter in the 5th layer, and we now try to see how this image we get out when we take in an image, how this filter image is activated. And you can see here that it seems like this filter is sensitive to images where we have faces, and we can even we can try some other examples, and you can see it's not only human faces, it's also animal faces. So it's kind of learned, and this is kind of emergent higher level abstraction, that to combine these simple edge detector color contrast filters in a subsequent layers to actually be able to detect images. And this is of course a good idea if you want to classify images into dogs and not cars. Then it's good to be able to pick up that there's actually a face in the image. And there's a very nice small YouTube video that demonstrates the toolbox that has been used to generate these images, and I will show that next.